Go.
Hello, I'm Tristan. We also have Wentao and Jehe, and we're a teammate team, and our project is Visual System for Autonomous Driving.
Autodriving is a hot topic in today's world, especially in deep learning. It includes detecting objects on the street and reacting to it, like detecting the pedestrians, vehicles, comparing their change in shape and location to predict the speed and the trend of their motion, or detecting traffic signs to help the driver to obey the traffic law. Image classifying and object detection are widely used.
So let me give an introduction about the whole picture for this project. The dataset we use is from Waymo dataset. We feed this data into a faster RCNN, which is short for Faster Region-Based Convolutional Neural Network. And eventually, this model can give us the prediction results about the objects, like where it is or what it is. For example, in the bottom right picture, the model will draw green boxes on the object it identified and show the name of the object. Like this is a car, this is a pedestrian. Let me introduce more about the dataset. So the Waymo dataset contains 1,950 segments, each span 20 seconds and collected at 10 Hz. They got 5 cameras installed on the car, on the front left, front right, side left, and side right. They also have 5 LiDAR systems. For the labels, they got 2D labels for all the camera images and 3D labels for the LiDAR system. If you go to Waymo's website, you can see there's almost 100 tar files on their website. Each file is 20 to 30 gigabytes. So you can see that's a huge amount of data. Since we only have very limited computing resources, we can only choose a subset from them and use cloud computing. We built the system based on Google Colab. So the Colab can let us have GPU accelerate and give us 30 gigabyte available disk and about 12 gigabyte of RAM. We choose 52D frames from the Waymo dataset. We need to notice that each frames contain a lot of information from multiple cameras. So in this way, we can still maintain a decent amount of the dataset.
Object detection is different from object classification since the length of the upper layer is variable. Some object detection algorithms like RCNN and fast RCNN use selective search to find out the region proposals. They're slow and time-consuming. Faster RCNN eliminates the selective search algorithm and lets the network learn the new regional proposals. We can see the structure in the next slide. The image is provided as an input to the convolution network, then generate a feature map. A separate network is used to predict the region proposals. The proposals are then reshaped and using region of interest pooling layer, which is then used to classify the image within the proposed region and predict the offset values for the bounding box. The classifier model used here is ResNet50, which is a convolutional neural network with 50 layers deep, where each layer consists of convolutional, ReLU, and batch normalization layers. 2 reasons for why we used a pre-trained model. First, the dataset is too large. On Waymo website, it provides 38 packages of training data. It takes several hours to upload just 1 package onto Google Drive. Second, the computing resource is limited. Colab will crash if we read more than 1 data frame. The classes we used in this project are pedestrian and vehicles, since the Waymo paper provided only the accuracy of pedestrian and vehicles as our baseline. Let's talk about results.
So the slide right here shows our results for a single frame. Every frame is composed of a total of 5 images from the various camera angles. The slide shows 3 of those images. The green boxes are those provided by our own model, and it seems to be doing a pretty good job. But if you look at the total vehicles we predict, which is 13, and compare them to the ground truth, which is 26, our vehicle accuracy is only 50%. This is because the images are robustly labeled. And if you look here on the first image, there's a car hidden right here beyond the orange building, as well as several cars all the way in the distance. These are not detected by our model. Our overall accuracy for vehicles is 47.1%, and our overall accuracy for pedestrians is 51.2%. This is compared to our baseline, which are the results published in the Waymo datasets, which is 68.4%/57.6% for vehicles and 55.8/52.7% for pedestrians. The difference between the slash are those level 1 images and level 2 images. Level 1 are considered hard to predict upon, whilst level 2 are considered harder to predict upon. Since we do not differentiate based on the labels, our results are more comparative to the level 2 labels, which are cumulative and include level 1 labels. That does it for our presentation. Thank you for listening.